slides we've set up are on the basis of the value of wood energy in the market and how to value your product and what it is that the value of that product is. Again, there's just some of the key objectives of the project, which is nearing an end now. Just in on 3 specific areas. There's the wood fuel producer, there's the equipment installer, and then there's some feasibility work being done on potential of introducing district heating into the region. The key objectives were to enhance and develop enterprises and businesses involved in the production of biomass fuels, maximise the use of biomass heating systems, and support the development of district heating. There are a number of biomass installer or manufacturers, and one of the outcomes of this project has been a database of boiler manufacturers right across Europe, which will be up and running on the website by the end of the project, the end of this month. So anybody interested in getting into supplying or installing boilers, there are a number of boiler manufacturers across Europe that have got good quality equipment. So there's an opportunity there, using the likes of our database, to get in touch with some of these manufacturers who may not have agents in Ireland and may be interested in partnering with somebody in that region. So again, that's bringing you up in the value scale. The pros and cons. So if you just get into fuel shipping and delivery, you have a minimum investment of money and time, you're not getting involved with banks, you're not getting involved in performance contracts, and you're just adding a little bit of value to your low value timber. The cons, again, it's the lowest level of added value, and depending on your model or your proposals going forward, a business plan, it may not be the answer for you. You may want to move to the next level, which would involve maintenance and upkeep of boilers. This is just the next level on the supply chain, where your partnership with an installer, so you're getting into the higher value of the product again. Again, the pros: increased customer confidence, potentially a bigger market if you can offer more to the one client. And then the cons: you're forced to partnership with other trades, and that can often lead to difficulties because they're not fully in control yourselves. So again, where to from here as a grower of timber or as a wood fuel producer? At what stage do you pitch yourself for adding value as a group? And are the members in the group are interested in forming their own bioenergy producer group? So within the cooperatives of private forestry growers, because that's where we see the resource of timber for the market, is the private sector forestry. Are there members within that group who are interested in forming a producer business model for the group and adding the value to the timber on behalf of the group? So again, why become a wood fuel producer? Secure jobs with labour, plant and skills. There's the local economy benefiting from not importing fossil fuels, which is a big drain in our economy. It's working well across Europe, where they've started on this road way back, but they've developed into some very big, large industries. And then there's lots of opportunity to create employment, which is key in the current climate. So, do we really need accreditation for wood fuel production? Again, we're asking the same question. Quality assurance, a method of ensuring and documenting that all the standards are met. So the quality assurance is the responsibility of the producer. And then quality assurance scheme or accreditation. This is where an independent third party monitors and checks that quality assurance is being carried out. So methodology for quality assurance. Select appropriate measures that give confidence to customers that the specifications are being realised. So you're monitoring and recording all of the time. And establish and document routines for separate handling of non-conforming materials in biofuel. So what's it all about? Again, it's to produce a quality product. If the production goes wrong and you haven't recorded it, how do you fix it? To prove to customers that you're doing your very best, you can't do any more. So critical control points. Again, going through the cycle right through to the customer. There's content size and content again, right through the system. So small trees, seasoning round wood, shipping small trees, storing the wood chip in a depot, transporting, and customer. Ultimately, all of these processes all feed into the quality control. these are some of the extra workloads that the UK, that Ben has associated with QA systems. So segregation of raw material, keeping and filing proof of felling licenses, keeping equipment maintenance and calibration records, extra monitoring of fuel quality before delivery, customer records, complaints, again record keeping relating to specific delivery. Traceability of timber is a big thing, particularly with carbon credits coming down the road. Evidence of an audit or a scheme from the scheme administrator. And in summary, the lack of accreditation does not necessarily mean a poor product, but it may mean a supplier has difficulty convincing others it's not.
But what is really interesting and important to notice and remember is the relationship between the heating value and the water content. As you can see from this graph, while the water content is increasing, the heating value decreases constantly with a linear function. And for example, if we dry a piece of wood from a 50% of moisture content down to the 10%, we can more than double the value of the heating value, if energetic content, let's say. It applies just if we do know the moisture content as well as the energetic characteristics and behavior of that biofuel. So basically, combining the information about the price of the reference unit, tons, cubic meters, and so on, with the energetic content of that biofuel, it is possible to easily calculate the price of the energy content. But on the contrary, if we can define energy price, a right energy price, as you can see from this graph, for example, 25 euros per megawatt, deriving it from other prices, the prices of other energetic sources, we can define this price for a constant moisture content and move up and down along the moisture content scale to define the right price of the ton of that biofuel, right? So, of course, the drier the biofuel is, the higher the price of the ton is, maintaining constant the price of the energy. So, we can say that knowing the quality of a product is a means to achieve the best use of already available natural resources.
What you want in chip is no long materials and all of fairly consistent size, so that you're not going to have issues with the material going through an auger system and that it's going to burn correctly. You don't want too much fines, too much dust in it as well. So it's important that the material has that consistency. Obviously the other major factor is moisture. It's actually quite a lot of variation in what moisture boilers will want. You'd have anything from 25% up to 55% for the larger boilers. And a lot of the larger boilers are designed to take wetter chip. So just because a chip is coming in at 50% moisture doesn't mean it's low quality. It's actually ideal for some boilers to have it at a high moisture content. And then obviously delivery is an important factor as well, storage as well we look at, in the fact that the chip needs to, it's alright producing it to a certain quality. There's no point in arriving at the site having got added moisture due to rainfall or it gets damaged, more so an issue with pellets, but it's important that the consistency that you want in your chip lands at the customer in the right format. Wood pellets then, some of the main issues there is dust level is probably the biggest one, and that really comes down to the manufacturing of the pellet, that it's robust, it's got that quality factor to it, it's hard, it's not going to get broken up too easily. And moisture content is a factor there, the fact that you get moisture getting into the pellet, it's a major issue because the pellet will break up if you have moisture getting into it. Generally the 8% figure is in or about right for pellets, if you have it around that level, you've got, it'll help keep the robustness of the pellet right, but the packaging is important to keep the product dry, to keep it intact, very important for those two facts. Again, you have to really look at the market that you're providing for here, it's the household market, and that you've got a clean product coming in, it's not going to leave a mess in the room for the user. When your material going out on a daily basis, having an on-site method of doing a moisture test is not a bad idea, and in fairness is something we generally like to see on the scheme. Now, this can be done very simply. On site, some of the certified people have basically an oven, and I'm talking about something you buy in Lidl for 35 euros, and a scales, and the weigh a sample, put it in for 7 or 8 hours at 107 degrees, take it out and re-weigh it and test the weight loss. Now, it's not the most accurate method in the world, but it does give a very good indication of where you're at. It's going to tell you if it's 30% or 20%. You know, and that's perfectly good for supply to customer. And this scheme is built around that will be backed up every so often by a test from Waterford. So you would take a sample, split it, test it in your system, test it through Waterford, and you've got a good idea of how accurate your test is.
The renewables that are used in heating in Ireland, it's absolutely dominated by biomass, with very small amounts then from solar, biogas and geothermal. Over a 20-year period, we have actually doubled our amount of wood energy use in the country. In 2011, we thinned just nearly 23,000 hectares of forest. In the next 18 years, we're going to be more than doubling the amount of thinning we're doing in forest as private forest plantations become of the right age whereby thinning is required. The profile of Irish forests is that over 60% of our forest resource is less than 20 years of age. So we have if you like, a growing resource there that can grow in line with the demands that we're placing on wood fuel supply. Our current management or harvesting system will extract somewhere between 30 and 60 cubic metres of roundwood per hectare. We've also identified that there's a substantial portion of wood in the trees, in the thin trees, that currently isn't taken. So that we can actually, not only have we got more thinning taking place, but we can possibly get more material from that thinning. Similarly, if we look at clear felling in Ireland, we currently clear fell around 8,000 hectares per year, and what we take from that is somewhere between 300 and 600 cubic metres of roundwood. Of course, we leave aside somewhere in the region of 100 tonnes per hectare of brash, another 100 tonnes per hectare of stumps. So again, there's a substantial residue resource there that currently isn't taken from Irish forestry. So what we feel is that we've got potential to expand and certainly supply wood in greater quantities to this emerging energy market. And I think it's an important statement of confidence for anybody that's going to invest, if you like, from an end user point of view, that there will be a supply of timber there. And so our research project is very much focused at examining these, looking at the supply chain costs and the productivity of different supply chains from these different resources, and coming up with basically the cost and the right systems to get this wood into the available for market. Part of our work programme is looking at storage trials then of different wood fuel assortments like roundwood, firewood, bundles, brash bundles and stumps. And then we're also looking at the characterisation of wood fuel properties, both by species and fuel type, and then also basically describing properties according to the European Solid Biofuel Standards. The one property when we talk about wood is wood as a fuel is we want to know the energy content. And again, the thing about the energy content of wood is it's very consistent. The key determining factor with wood is the moisture content.
My work concerns 6 tree species of commercial merit in Irish forestry. 3 of those are broadleaf, ash, alder and birch, and then 3 coniferous species, lodgepole, pine, Norris spruce and Sitka spruce. So the most important parameter of all in this context is moisture content of wood, as is already well documented, expressed as a percentage of total weight of wood. So when you discount the moisture in wood, what you've got left is actual living organic dry matter, otherwise classified as biomass. And basic density is the expression of this dry matter per unit volume. And generally the greater the density you have, the more combustible dry matter present, meaning a longer burning time. Now the benefit of having lower moisture content is say ash for example, is that it's going to take less time to season down to the suitable moisture content of 20%, provided the stack is covered and it's getting plenty of air going through it to remove the moisture. So out in the field, the methods used for characterising wood biomass are identical to those for quantification. So they complement one another, and when you're out in the field, it costs a lot of money to conduct the work, so you might as well try and get as much data as you can. So therefore, quantification of all three components are part of this investigation, and that includes the stem loads of the so-called merchantable section of the stem, which is a hallmark of forest management, the growth of trees to produce logs to be sold to the sawmills, and then residues that make up the remainder of the total above ground biomass profile were once considered as being of no use, but now possess potential for conversion into energy. So, just some results. I'm just going to isolate sickness spruce here, and there's an accurate breakdown of the total above ground biomass profile, and as you can see, 57% is in that so-called merchantable stem, whereby the remaining 43% come in the form of the unmerchantable stem sections incapable of producing logs, branchwood, foliage and dead branches. And furthermore, 28% of that 43 is actual wood for conversion into energy. And so, there's the actual kilogram figures. And remember, dry matter kilos meaning no moisture. And so there's much more biomass to exploit. So the mean total woody biomass at age 17, and the stress age at 17 is roughly 85.3 kilograms. Now, if this is pitted against intrinsically better quality species like ash at age 17, there's a hell of a lot less there. There's 3 ash to every sickest spruce almost.
One thing that we can't get away from, whether we want to dry or not, is that when we deal with using wood as a fuel, we're going to have to store it. We're storing it at various points. At the harvesting stage, it's stored at the forest roadside. It's stored in depots, and then of course as end users we have to have some storage as well. So storage is unavoidable, I guess, in the supply chain, and typically it happens at various stages. So what we've done in all cases in our storage files is we get a sample moisture content at the start and a sample moisture content at the end, and we basically see what's happened in between during the storage period. When we look at all our work where we looked at assortments that were stored in the forest, of course it's stored in an environment where they're surrounded by trees. So what that means is literally there's very little airflow and also typically quite humid conditions. And the reality is the results reflect that, is that we've seen relatively little change in moisture content even over substantial periods of time. And end users that are looking for wood chip that's at 30-35% moisture content, this type of drying system just isn't going to be sufficient. So what we looked at as well is, okay, what happens if we take wood out of the forest and store it in depots? And we started storing material at different times of the year to look at the seasonal effect, and so you can see that in all cases, the moisture is starting at between 50 and 60% moisture content, and typically the curve is, certainly in the spring and summer, is a rapid decrease and then a slowing of the drying rate. And what's maybe most interesting is this curve here, starting in December, is that we get very little drying, and then, of course, as we come into the following spring and summer, we get more rapid drying. But the final interesting, if you like, part of that work was actually looking at what moisture content we were able to achieve, even in Irish climatic conditions. And we're noted for our rain, but we can still achieve moisture content of about 20%. So certainly, we have the capacity to dry material to a variety of suitable energy end uses. What that work has also allowed us to do is develop a forecasting model for roundwood drying in a depot situation, and we've developed that model based on evapotranspiration and rainfall. So what the model does is it basically says is if the moisture content is say 60% now, what will the moisture content be after 10 days, depending on the evapotranspiration and rainfall during that 10-day period. And what that's allowed us to do is to look at then the length of time to get a moisture content from 55% moisture content down to 30% moisture content for different times of the year and different areas. So what it means is that typically 4 to 6 months is sufficient in most cases to dry roundwood down to 30% moisture content. Of course, in the right location and if it's stored in good condition.
With the oven dry method itself, when you're getting down to the testing stage for the actual determination of the moisture content, you're using it in an oven at 105 degrees, basically until you're drying the moisture from the wood until you reach a constant weight, which can take between 24 to 48 hours. Just going on to the standards out there for the electrical methods, which would be moisture meters. You're basically looking at there's two. The first one there is for estimation by electrical resistance method, and the second then is just by estimation by capacitance method, which is basically the two kind of main electrical methods that you'll be using for moisture meters. First of all, the roundwood trials, the two meters that we used were the humimeter, BLW, and Protometer, Timbermaster. Basically, the two types are both resistance meters. Here is just to show you here from doing an over test, and you can see the difference in the means. Basically, over the 377 discs, the humimeter, BLW, the outside measurements, the mean of all discs moisture content was 42.46%, and the mean of the humimeter outside bark measurements differed by just 1.1% moisture content over the whole sample of the discs. So the proposed methodology is just based on a sampling type from chapter 4 of the timber measurement manual published by Waterford. So basically what you'd have is steak or small soil, so we would be using pulp. So applied that, we would be having a sample size of 40 logs, and if it was taken from a lorry load, it says within that system to take samples either taken from the top or the bottom of the lorry. So what we would have here is a sample of 40 logs, 40 measurements, 1 per log, at the 1.5 metre mark in the middle of the log, and then just calculate the mean of all the metre readings, and it should give you kind of plus minus 2 to 3% moisture content determination of the load. So basically, just a conclusion. There are meters available that are accurate and very good for repeatability as well, for moisture contents, for comparing to the oven dry reference method.